Hey, all right, that's better. Hopefully, we won't get blasted with a lot of noise again. Um, Thank you very much. It's great to be here. This is my first time in Medellin. If they bring the bingo contest back, you can still use me as an answer for that. I also know how you can get the Antarctica question answered if it does come back. So I can tell you. But I'm the VP of engineering at a small startup called Walu Labs. I'm also a member of the core team for a programming language called Pony. And as folks who were at the speaker dinners last night can attest, I am a GENERALIZE lover. There's some information for me on various Twitter type things. I don't have Facebook. Also good for a bingo answer. There's a lot of information that's going to go through this talk pretty quickly. So there's a GitHub archive which has links to basically everything that I reference. So if you don't know what it is, that's fine. Not everybody's expected to know it all. You can go there, take the pictures. This will also be at the end. I added this at the beginning because I noticed that like slides at the end basically exist for about 10 seconds before they get replaced at best. So that probably wouldn't have worked out. Today's topics, data corruption, concurrency, data races, shared values, and atomic operations. If you don't know what all of those are, don't worry about it. In the end, even though I don't really talk about it too much, what this talk is really about is scaling data handling applications. The problems that are going to cover in this, there are a number of them. Each of them could be their own lightning talk. So this is an overview talk to get like folks who might not know a whole lot about the topic more familiar with it. So just out of curiosity, how many people here would raise their hand and say that they feel like they know a lot about distributed systems and data handling? Awesome, great, great. Then this talk is for all of you who didn't raise your hands. That's wonderful. Something that you should know, there are going to be a lot of generalizations in this. I like to call them lies, but they're helpful lies. The topic, that's in here, you could talk for hours on it and still not really cover it. We have 30 minutes, so if you go out and you tell people exactly what I said, they're probably going to tell you all the ways that it's wrong, but it doesn't matter because the important part is that you can come out of it, go to that GitHub repo, and start really understanding a lot of the contents that's there and start following through. So, first lie. Our most popular architectures can be traced to web applications. This isn't really necessarily true. There's a history that goes further back than that. But most people these days are building web applications, so it works nicely. And I also started my career around the time that web applications started happening, so it makes it easier for me. When we say a web application, usually talking about something that looks like this, right? If we were to diagram it, we have our web app, we have our database, and they're communicating with each other in some fashion. Pretty much any web application ends up looking something like that, even if it's 18 microservices that all have to talk together and are being deployed by continuous deployment, or if it's, your simple, like a WordPress blog or whatever, right? In the end, they have the same core interactions with stuff. And if we were to make that a little more detailed, what we probably have is something like what we were saying is, hey, we have a request, goes to our application, which is going to communicate with the database in some fashion. It's going to do something, it's going to come back to the application, and then we're going to send a response out, right? Or maybe a little more detailed is, hey, there's a web browser here, and it's going to send something off to a web server, which is running some developer code, to the database, then back around and out again, right? Probably most folks in this room have worked with something that looks like this. Probably most folks in this room are going to potentially introduce data corruption like we're going to talk about. Don't worry if you have, because I've done it many, many, many times. Our simple web app is a distributed system. It's crossing machines. It's crossing from one process to another. We have it at minimum. We have our web app. We have our browser. We have the database. Lots of people like to get up on stage and tell you that distributed systems are hard. I'm here to tell you that distributed systems are easy. If you tweet a picture of this, it'll make a lot of people angry, so please go ahead and do that. I like to make people angry from that kind of like, not really mean, just kind of having fun with them. If you missed it, oops, too bad. What I would say is that concurrency is really the hard part. If you have distributed systems, where there's only one browser ever doing anything, one client doing something, it's really easy. It starts to get difficult when you start to add in more clients, more browsers, and you want to scale a system. That's really where things are getting hard. When people start talking about distributed systems being hard, what they're really talking about is scaling them is difficult and making them work. And probably, the rest of the talk in some ways is a justification of that statement. So let's go back to our first diagram here. Most diagrams, when we put stuff together, if you ever do architect type stuff, you'll do lots of diagrams like this. There'll be boxes and squares everywhere, and there'll be these little lines connecting them, and everybody really they spend a lot of time talking about the boxes and squares and everything, and they never spend any time talking about the arrows, which is too bad because the arrows are what's the actual really important stuff in all of our systems. It's the interaction between the different components that we have, and yet, we put them in there just like a small little thing here, kind of a grayed out color in the diagram, it probably should, be something more like, hey, woo, all right, you're the star, yes, awesome. But we don't do that. So anyway, I want to talk about this using an example application. This is going to sound really simple and contrived. Don't worry, it is, but this is also a thing that people actually legitimately did back in the 90s, which is one of the reasons why I wanted to use the 90s set for this, is that we did this great thing where we had pages where you could go to them on a website, and it would show you how many times a page had been displayed on this website. Great, great, great fun, like counters. It was really exciting. Truly revolutionary times for computers. So basically, what an application like this does, and it looks an awful lot like many other web applications, is it's going to go ahead and it's going to read the current value of the counter from the database, right? And we're going to add 1 to it because we want to update the value, as each time somebody visits, and the page gets displayed to them, we want to increase that. And then we're going to write that value back to the database so that it'll be useful later on. It's not just going to go away when our process ends. And then we're going to return the value to we're going to return the new value to the user. So if you come in, you're going to see number 1, next person's going to see number 2, next person's going to see number 3, etc. Really, really simple web application, right? So can you put your hands up if you saw the data corruption in that application? Oh, all right, we got a couple there, not too many. All right. Again, here it is. 4 steps. This can corrupt data. We're not going to get the results that we're really expecting. Our counter's not going to work. Why? Well, let's add some concurrency to it, because that is the hard part in everything, right? What if we put 2 requests side by side, and we had them like this? Now we have the interaction side by side. Can anybody who didn't have their hand up before, can you see how this would corrupt the data? All right, we got a few more folks. Awesome. For folks who don't, I'll tell you this, we don't know what the final value for this is. For those 2 requests, the second person who comes in, we use the scary air quotes there for those. I love scary air quotes. My entire life is about putting scary air quotes around things. If you follow me on Twitter, you'll see that all the time. And the value could be 1, could be 2. We don't really know. We have no idea, and we can skip this slide now because I already said that earlier. So, again, back to this. The interesting thing here is that the values that are on the left-hand side, the operations that are going to happen on the left-hand side and the operations that are going to happen on the right-hand side, we don't know what order those are going to happen in, right? These are concurrent things where they're individual steps which can be executed separately, which are going to happen. And what we end up calling this is we call these interleavings, right? Where, for example, this is one possible interleaving of these 2, right? Where we got the interleavings for request A in blue and the interleavings for request B in orange. And if you follow these interleavings through, following the algorithm we set up, you can see both of the users for this are going to see the value 1, right? Which is really not what we expect from our simple thing that we had there. We expect one person to get 1, the next person to get 2, right? With a different interleaving, like this, where everything happens for the first request, and then everything happens for the second request, we're going to get 2, which is what we expected for that second person. But, again, we have an interleavings where that won't happen. Here's yet another interleaving where they're still mixed between the 2 of them, but we're going to end up with 2. And the important thing of this is that in order for us to get the correct result based on how we set this up, this write new value to the database, for whichever the first one is that comes in, has to happen before read current value from database for the second one. And if that does not happen in that order, then we're going to get results which are potentially going to be surprising to us depending on how we're thinking about it. And the term for something like this is a data race, right? We have a couple different things which are trying to access the same data, and we're going to get something unexpected from it. There are 4 basic components to a data race. First one is a shared value, right? Second one is concurrency around that. Third one is we need at least one thing which is actually writing changes to the shared value to have any sort of data race. And the fourth one is non-atomic operations. It's probably the most complicated bit. We're going to go through all of them. In our particular case here, our database is a shared value. We have a counter which is stored somewhere in a database that multiple things are working on. If you've ever heard people talk about how like shared values and global values in like a regular program that you might write like Python or something can be bad, same thing with the database here, right? We have concurrency because in this case, for our simple example, we had 2 requests, right? 2 requests there. There's an awful lot of writing going on there. Not anything particularly interesting for that, it's just a lot of writing. And our incrementing that we're doing isn't atomic. How many people know what atomic is? All right, spend some time, but not a ton of time on it. So I'm going to call atomic, and by the way, this will get you in a lot of trouble depending on who you talk to, so maybe keep this definition here. This is sort of a weird, perverted database definition of it, kind of. An operation is atomic if it's isolated from other operations that are happening at the same time. Maybe that's meaningful, maybe it's not. So let's go back to our interleavings and look at this. Again, here was this was one of our set of interleavings where we ended up with an incorrect value. So the reason why we had that incorrect value is that what we wanted to do was we wanted to increment, right? But we incremented by taking 3 steps which are going to happen individually one at a time. We're going to read, we're going to add 1 to it, and we're going to write. We're going to write that value back to the database, which it's very much true, but each of those things is an individual thing which can happen separately. When we're saying that we want something that's atomic and isolated, what we mean is that when we're putting together our interleavings, what we really meant was something more like this. Those 3 things should really just be increment current value. If we have that, then when we do any sort of interleaving for these, right, we're incrementing our current value. We're no longer going to have this problem where we're going to potentially have a data race for those because we're doing increment current value and then increment current value again. And the action of incrementing a value will not allow like any of those other details to leak out like, hey, I can read the value basically partially through what you're doing then, right? Okay. And so that's one little bit right there. That's the atomic, right? What's interesting is that our algorithm, when we put together the first one, where we have those 3 steps in order to increment the value, when we add more writers, we actually come up with yet another data corruption problem which exists right there in that as well, right? So this is a fun one. Okay, so what we have here is we have 3 different requests which are all executing our original algorithm. And as we go from left to right across the slide, we're advancing forward in time and certain operations happen. So in our first bit right here, we have request A and request C both execute the first part of our algorithm, which is to read back the current value of whatever the counter is, which in this case is 0 for each of them, right? Then request A is moving a little bit faster than some of the others. It does the addition so that it gets 1, and still moving faster than the others. it then goes ahead and it's going to write this value back out to the database so that when this is done executing there, our current value in the database is now 1. All right? Seems to make sense. Then request B, which got queued up and was waiting for whatever reason it might be, reads that value back from the database, and it reads 1. Right? When it adds 1 to it, right, we end up with 2. This is great. This is one of our happy interleavings that is going on right here. So that when we go ahead and rewrite this back to the database, we're going to get a value of 2, which is exactly what we'd want to have happen. Perfect. It's beautiful. Problem is that we had request C down here, which is kind of the slow poke. I don't know. Maybe it's running on an underpowered AWS machine compared to the others. Who knows what happened? But something happened. Request C is running slower than the others. And finally, after waiting a while, where it read 0 back from the database, it's now going to add 1 to it. All right, so we get 1, and when it writes to the database, it's going to write its value 1 back in there. And the database value just decreased back to 1, which, for a counter which is supposed to count every person who comes into the website, not really exactly what we're looking for there, right? That should be 3. Would everybody agree that 3 should be the end result of doing all this? So what this is called is last write wins, right? And this is a perfectly wonderful way to potentially solve problems, when you're in a distributed system for data, except that, last write wins kind of indicates by just by its name that it's like some writes lose, right? That write where we wrote 2 into the database, which was good and correct, it ends up losing because it's like it didn't even happen. We went back to 1 because of how we put the algorithm together. Or in my kind of jackassy kind of way that I like to say it, hey, last write wins is a fancy name for let's corrupt some data, right? And the problem here is that we have this shared value. It's a place in a database, which is shared across anything that's accessing it. And whatever we update it to, it's going to be. So if some slow client somewhere updates it to a value which is not really meaningful or actually valid anymore, that's still going to be what it is, and it's like nothing else ever happened there. This is actually like core to almost every web application that I've ever gone into any company and ever worked on, right? It's just how stuff gets done. Read something from the database, you change it, you write it back. Don't even check to see if it's changed during the intervening period of time. It's just like, hey, my write's 1, right? And this is built into almost all of our popular architectures for scaling. We have a database where we're using as a shared value, and we have concurrency, which is the entire point of our scaling, right? Is to throw as many things as we can in front of a database, and in general, in a lot of cases, hope for the best, right? These problems are everywhere, like so many of these things. Serverless. Everybody know what serverless is, more or less, right? It's effectively basically like this. Maybe you've heard it called functions as a service, which usually, most people, it's like functions, and oh, okay, function is a thing technically in math, It doesn't have any state, it just takes some input and returns some output, but that's not really what people are using, functions as a service for. They have something where it's taking a whole bunch of web requests in that get spun up by like AWS using Lambda or whatever, and it's writing it off to a database somewhere. And if we were to do our simple page counter using functions as a service as the simple hello world type thing, which an awful lot of people spin up, we're going to have exactly the data race that we had earlier, right? Stateless. Everybody loves to talk about stateless. Stateless is basically right now in the back of my mind. I'm just thinking stateless, and I'm kind of laughing hysterically because nobody really actually wants a stateless application. What they really mean is that I don't want to have to think about the state, which is just in a database somewhere else. And I want to be able to scale my thing out without thinking about these harder problems that are here with how do I manage the state. And an awful lot of stateless architectures end up looking like basically our simple web app. We expanded it out. We have the database. How do we deal with this? Well, we can scale the database up some, and then we can just throw a whole lot of processes in front of it, a whole lot of web servers to be able to handle lots of stuff. Sometimes this gets called shared nothing, and usually, this can be in there as well, right? all of these feature shared value, which is the database, and concurrent writes. In every single one of them, unless you're really working in it, right? Oh, don't worry, that 10 minutes we're gonna be done long before that. Has this data corruption baked right into the core of it, right? It's there and it's in it, right? So, question is really, what can we do? And although I have 10 minutes, I really didn't think I was going to have 10 minutes at this point, but I got up here and I started talking a lot faster than I expected to. So we could have covered a bit more of this, but in the end, really, what we need to do is we need to change the data race recipe, and this is completely doable within almost every single one of those architectures. But you actually have to stop and think about them, right? So we need to get rid of at least one of these things, potentially more than one of them, depending on how we want to go about tackling this. We either need to not have shared values, we need to not have concurrency, we need to not have writers that are writing to the shared value, or we need to make sure that every single one of the operations that we're doing is somehow atomic, right? One of the great things is that an awful lot of people can write a ton of web applications, do exactly what we showed, and they will never have a data corruption problem because whether they realized it or not, they remove the database as a shared value. Just because you're doing this and you're writing something back to a database. Like, let's say that you have an application where each individual user has their own account information and everything, and they're the only person who ever changes it, then there's probably never going to be two writers trying to make a change to that data at one time. Like, a giant chunk of web applications are exactly like that, where probably the only way that this could ever happen is if the user is trying to change their account info and somebody who has admin privileges as well is trying to change it, right? And whether they realize it or not, those people kind of change the recipe there a little, right? But if that's not your application, then there's some other things you're potentially going to have to do in order to address it, right? Because what we're really aiming for here, if we don't want to have corruptions data, is we want to have some concept of a transaction, like there is in a database, where these three things that we want to do for this algorithm need to happen all together or not at all, and they need to be isolated from one another. We need to have some sort of consensus amongst all of the people who are using the system, right, as to what the value actually is. And we want to have some kind of fault tolerance so that if something fails, right, that everybody will still continue having the system working. And in real world architectures, usually you can do two of those three together. Pick them. I'm not going to do, but getting the third one is going to be kind of difficult, and you're going to have to make trade-offs. Like, one of the easiest ways to address this is now basically heresy in building web applications, and has for a long time, is that if you did SQL the right way, in your database the right way, you could avoid this by using stored procedures, for example, and transactions on your database. And you no longer have this problem. You can fix it there. On the other hand, you now also you've created a bit more of a problem when it comes to scaling your database, and that could be a problem, right? You could use distributed transactions. I say you could because I also have talks where I talk about how awful distributed transactions are for scaling, etc. But if your trade-offs are there, it's legitimately something you might want to do. You can synchronize data access, and this is kind of a hand wave because there are 1,000 different ways that you could do this. But you could synchronize data access. There's a model of computation called the actor model, of which there's a variation of in Erlang, in Elixir, in Pony language that I work on, which can provide some synchronization to data, which you might be able to do and start building a system using that. You can use locks. Like, this exact same problem we're talking about here exists if you're running a multi-threaded program, right? If you're writing something in C, C++, or whatever, you have multiple threads, and you have shared data that you want to update, you put a lock around it. You can do the same thing in a distributed system. You might not want to. There's certain bad trade-offs there, but I'm not being judgmental here. You could do something that's called event sourcing, which you're going to have to make a lot of other changes, but it can start to address things like this. There's also a pattern for splitting your reads and writes from one called CQRS, which is a link to in the GitHub, which would allow you to potentially do some sort of synchronization around your data. You could decide that, you know what, Paxos or Raft is really what you want to get into, and you want to use a consensus algorithm. And you might even be able to get, better trade-offs than you thought you did, by going off and reading Heidi's paper that she talked about yesterday. For that, on the other hand, you might not want to use a consensus algorithm. Perhaps you want to use concurrency-friendly data structures. The biggest example of this are CRDTs. These are data structures which are basically designed where they have rules built into them so that you can have multiple different writers writing into it at the same time. And there'll be rules for what do I do if like two things try to change the same data. There's going to be some type of like knowable rule for how this happens and you build your system around that, right? In the end, for me, I think the most important thing from this is that you should communicate operations that you want to do on data within a system rather than the values themselves. And like so in our page counter example, right? If what we've been actually communicating from in some fashion from whatever our clients were to our shared server that's there operating stuff, if we'd been saying increment 1 instead of change value to 2 or change value to 3, right? We wouldn't have had this problem at all. And what ended up happening is in a lot of ways, and this you see this a lot, is we tend to take things where we do them in a single process. Like if I was just writing a Python script and I had some value and I wanted to update it, by adding 1 to it, I would basically do what we did in the database scenario, where it's like, oh, right, I got to know what the current value is, I got to add 1 to it, and then I'm going to, put the value back. But that doesn't really capture like what we wanted to do, which was increment 1. So yeah, operations over values. And that's really all I have for you today. Again, there's the slide. Let's see. If I keep talking for a minute, anybody who didn't get the picture before can probably take it again. So is anybody in a picture of that? All right, I'll just keep talking. Awesome. All right. Yep, definitely. So if the bingo does continue in Antarctica, there are 2 organizers of the conference who are not here who can be your answer to that. That's your clue. All right? Thank you very much. Have a good day.